Right, hi guys. So now it's getting a bit closer to exam period season. We thought maybe we could upload some short, like maybe intense videos, just dealing with like different harder topics in mathematics. So today I'll be starting off with differentiation. As I said, it's going to be like the harder topics. So like stuff like the product rule, quotient rule, you guys should know already by now, right? So I'm not going to cover that. Okay, we're just going to be looking at some maybe difficult topics, questions in each topic of differentiation. So first things first is a chain rule. Right, so chain rule, you might have seen this equation a lot in the textbook, and maybe your teacher has used this formula to show you how to use a chain rule. But just a quick tip on how to use a chain rule, it's like a three-step process basically, the way I think about it. So first of all, use the chain rule when we have like something raised to the power, right? So in this case, let's say cos x to the power of 5. So you could say that normally u is cos x, differentiate u to get du by dx, and just apply this equation. But the way I go about doing it is just like a three-step process, as I just said. First step is bring the power down. So in this case it's 5, so I bring that down. Second step, I differentiate the function. So in this case cos x, the derivative of cos x is sin x. And the last step is I rewrite this whole function out again, but I minus 1 to the power. So it was 5 here, so now it's going to be 4. It's just like a three-step process. It's maybe a big, I don't know, you guys probably have seen this before, but it's just like a quick way of applying this chain rule. Let's try this one here as well, just as a quick practice. So this is 1 over 3 plus cos 2x. I can rewrite this as 3 plus cos 2x to the power of negative 1. So when I differentiate this, as again, the power comes down, in this case negative 1. I rewrite this out, I differentiate this, so I get minus 2 sine 2x. And then I rewrite it all out, but I minus 1 to the power. It was minus 1, minusing 1 again will be minus 2. And obviously you can simplify this a bit, but this is basically how you apply the chain rule. Alright, the next differentiation topic is implicit differentiation. You guys should know it. This is when we're differentiating y terms, anything like with a function in terms of y. So the best way to do it is whenever you're doing that, just always place dy by dx behind it. So for example, like x squared is equal to tan y. I can rearrange for y is equal to, but that's a bit more difficult, so I can just differentiate straight away. X squared, that becomes 2x. The derivative of tan, just think of it like tan y, alright? So that's going to be sec squared y. But because I differentiated the y term, I should always place a dy by dx behind it, like such. Okay. Let's look at this one here, a bit more difficult. We've got quite a few terms, okay? So 3 to the x. Hopefully you guys know by now how to differentiate anything like a to the x. The derivative of a to the x, you guys should hopefully know, is a to the x ln a. Okay. If you don't know this, you should maybe look back into your notes and work, make sure you are comfortable with it, because they could ask you to derive it. Okay. So in this case, it's going to be 3 to the x ln 3. We have this y term here. Just imagine just differentiating y as if it was x, so it's just be 1. However, we differentiated the y, so I place the dy by dx behind it. This here, we have x times y, so therefore if it's times, we should use a product rule. Let's set u as minus 2x, v as y, therefore u prime will be minus 2, and v prime just differentiated that y 1, but it's y, so we place the dy by dx behind it. So this will be minus, so u v prime minus 2x dy by dx plus vu prime, so minus 2y. Obviously we could leave it here, but they will probably want you to get dy by dx on its own, so let's rearrange for dy by dx. 3 to x ln 3 plus 2y, I can factorize this straight away, so 1 minus 2x dy by dx. And all I have to do is divide this to the other sides to get dy by dx like such. So 3 to the x ln 3 plus 2y over 1 minus 2x like this. Okay. But the important part, this last part is just rearranging, but the important part is just differentiate any y terms as you would do, and just replace dy by dx behind it. Okay, the next part is parametric differentiation. This is when we have parametric terms. So for example, like x is in terms of some function t, y is in terms of a different function g of t, like this. As you know, hopefully you've done the parametric equations topic, you should know that you can make a Cartesian equation by replacing the t's. However, if they're more difficult, for example, x is like sine cubed t, let's call y like maybe like x squared, no, so not x squared, sorry, t squared, okay? Then we could replace it, but you could also just differentiate it individually. So dx by dt is equal to chain rule again, 3 differentiating sine is minus cos x, cos t this time, and then sine minus 1 to the power, in this case sine squared, and dy by dt, that's just 2t like this. And so you can see here is dy by dx would be equal to dy by dt, in this case 2t, over dx by dt, so minus 3 cos t sine squared t like such. I don't think parametric differentiation is any difficult, it's just make sure you know all the rules and the derivatives. Okay, the next one is inverse trig differentiation. This is quite one of the harder topics because these formulas, they are given in the formula book, okay, so you can use them. However, you should also be able to derive them because they could ask you for that, okay? So let's show that using this equation, this question here. Curve C has the equation x is arc cos y squared. Show that the derivative is this. So let's start off with x is equal to arc cos y all squared, okay? There's many different ways of dealing with this. You could maybe rearrange for y, okay? However, that's going to make it a bit more complicated. So what we can do is just do implicit differentiation. That means we can differentiate each one separately, okay? So let's bring the square to the other side. So x to the power of half is equal to arc cos y. Now this here is going to be very important. We're going to have to use this later on, okay? So let's keep a note of it. Now I differentiated each one separately. So x to the half, that's going to give us 1 over 2 x to the negative a half. And differentiating arc cos, well, I can just use this one here given the formula booklet. Just replacing this x with y. So it's going to be minus 1 over the root of 1 minus y squared this time. And because we're differentiating a y term, I remembered I placed a dy by dx behind it. I can now rearrange for dy by dx. So dy by dx is equal to, we're going to bring this to the other side, so minus 1 over, minus root 1 minus y squared, all over 2 root x like this. I could leave it like this. This is technically the answer. However, they want it all in terms of y, in terms of x. As you can see, it's all x's, right? We have a y term, so we need to replace this y term. The way we'd go about doing it is going back to this here, the one we start, because this tells us the relationship between x and y. As you can see here, x to the half is arc cos y. Therefore, y is equal to cos x to the half, which we can now replace back into our derivative. So dy by dx is equal to minus 1 over y squared is now cos squared x to the half over 2 root x. And this is the answer they wanted earlier. Okay. So as I said, you need to be able to derive these, okay? So maybe we can just do a quick example question. So let's maybe try a different one. Let's say y is equal to arc tan, let's go 2x. Okay, so you need to be able to derive this. There are certain steps which should be very, very clear and important you should take note of. So first things first, we get tan y is equal to 2x. This is the very first step which you should take a mental note of. This is an important step here, okay? We're going to need this later on, so maybe just be aware of this now, okay? We then differentiate as normal, so this derivative of tan y is sec squared y. Remember, we differentiated y, so implicit means we have to place a dy by dx behind it. And that's equal to 2. Rearranging for dy by dx, that's just equal to 2 over sec squared y. Once again, we can leave it like this. This is the answer technically. However, we want it in terms of x everything. So we have a sec squared y, so we should replace it into x. It is tempting because we know sec is 1 over cos, right? So I could maybe simplify this to maybe 2 cos squared y. It is tempting to do this, but we don't want to do this, okay? What we want to do is find an identity that involves sec squared and this tan, the one we made a mental note earlier. You should hopefully know that 1 plus tan squared x is sec squared x. So therefore I can say that this is equal to 2 over 1 plus tan squared, in this case y, right? Not x, okay? Now we go back to our initial one here. Because y, tan y is 2x, and we have a tan squared y here. So I can say that is 2 over 1 plus 2x all squared. And further simplifying here, 2 over 1 plus 4x squared, like such. Okay. So when you're differentiating inverse trig terms, the important steps are this one here, identifying how to relate y and x. And the second one is this one here, the identities that can relate this derivative with our initial one here. Okay. Alright, the next part we're going to deal with is rates of change. Now, when we're dealing with rates of change, I want you guys to just remember a couple of very important terms, okay? The first one is the word rate. Whenever you see the word rate, this you can automatically think of something over dt. Okay, so whenever you see the word rate, always think of something over dt. They might say a rate of anything, right? This is always going to be something over dt. This rate of something is going to be on the top. So it could be a rate of height, rate of volume, rate of weight. It could be literally anything. But the important word is rate. That means something over dt. The next important words are increase or decrease. This just means that the derivative is either going to be a positive for increase or a negative for decrease. Okay, so that's another important thing to notice. And the last one, it's not in every question, but the last one to also note is how many variables there are. Okay, so this we will show using this equation here. Right, so let's look at this. An inverted conical funnel is full of salt. The salt is allowed to leave by a small hole in the vertex. It leaves at a constant rate of 6 centimeters cubed per second. So let's deal with this first here. As we said, we see the word rate. That means something over dt, right? Now, something over dt, that's going to be, and it says leaves, okay? Leaves is similar to decrease, right? So that's going to be negative, right? So it's something over dt is going to be 6 centimeters cubed per second. At first glance, it's very difficult to note what's going to be on the numerator in the top part, right? In this case, if you get confused, always look at the units, because they will give you the units. As you can see here, it's centimeters cubed. Centimeters cubed is a unit for volume, right? So it means that dV by dt is negative 6 centimeters cubed. Okay. Given that let's look at the next part. Given that the angle of the cone between the slanted edge and the vertical is 30 degrees, show that the volume of the salt is this. So we need to show that volume is 1/9 pi h cubed. Let's do a quick drawing just to visualize what's going on here. So this is a cone. They're telling us that the angle between the vertical and the slanted part is 30 degrees. And let's call this height h, and let's call this part radius. What we should note is that the volume equation for a cone is 1/3 pi r squared h, like such. As you can see, it's slightly different to this one here, okay? That's why we have to look at how many variables there are. In this case, there are two variables, r and h. They both change with time, but as it decreases, r will change and h would also change. So we need to try and replace it to make it one variable, as we can see here. Luckily for us, if you look at the drawing, it's like a right angle triangle, right? So I can just say that tan 30 is equal to r over h. And therefore r is equal to h tan 30. Tan 30 we should know is √3/3 h. So if I replace r squared into here, then I get volume is equal to 1/3 pi, r squared is √3/3 h all squared times by h, which will give us the one they want, 1/9 pi h cubed, like such. Alright, next part. Show that the rate of change of height of the salt is inversely proportional to h squared. Once again, important word to note, rate, right? So that means something over dt. In this case, what is it? Well, the rate of change of height, there is a dh by dt, and they're saying it's inversely proportional to h squared, like this. So that's what we're going to try and show here. Okay. For this part, we need to create a differential equation. So we're trying to find dh by dt. We know dv by dt we saw earlier here. So we know dv by dt. So to get dh by dt, we need to multiply by dh by dv. We can also say that dv by dt times dh by dv, I can say is that 1/dv by dh, treating it just like a fraction like this here, right? So we just need to find dv by dh. Luckily, we found v earlier. V is this. So therefore, dv by dh is just going to be 1/3 pi h squared. So therefore, dh by dt is dv by dt, which is -6, multiplied by 1/1/3 pi h squared, which just gives us -18/pi h squared. And the fact that 18 and pi are both constants, it means that dh, we've shown that it's dh by dt is proportional to, or is inversely proportional to h squared. Okay. So when dealing with these questions, just always make a note of these important words they give you in the question. Okay, so the last part of differentiation I will deal with is maximas and minimas, and point of inflections, but that seems most difficult. Okay. So first of all, maximas and minimas. Well, we all know that maximas and minimas occur when the gradient is 0. So that means when dy by dx is 0. So whenever you have a function, just differentiate it and make it equal to 0, and then find the x. That should be fairly simple. But how do we know it's a maximal? Well, maximas is when the second derivative, we differentiate again, is less than 0. And minimas, as you would expect, the second derivative is going to be greater than 0 like such, okay? So this is how you just show the maximus and minimus. I don't think it's going to be difficult, this part, so we can just move on. The problem is when we get that the second derivative, if we work it out, and it becomes equal to 0, okay? This is when we have to deal with something called a point of inflection. What's a point of, well, first of all, a point of inflection occurs when the second derivative is equal to 0. But it's also known as when the shape of the concave and convex changes. I think hopefully you guys know what the difference is. Concave just refers to a shape. So this part here we can refer to as a concave shape. And this one we can refer to as convex, okay? You might also, I don't know if your teachers use concave and convex. They might use concave up, concave down, but it's the same meaning, okay? So it just means when the concavity changes, okay? So the way we show it is, well, yes, we can say it's equal to 0 and say it's point of inflection, but you won't get the marks in the exam. What we have to do is find the second derivative and show that it's less than 0 and it changes when it's at the point of inflection or either side of the point of inflection, okay? It might be a bit difficult to understand, but let's show you using this one here. So the curve CS equation like this. Find the exact coordinates of the stationary point on C and determine its nature. So we know a stationary point is when the first derivative is equal to 0, like this. So I can just differentiate this here. Is the chain rule, the product rule. So we have e to the x, we have x squared minus 2x plus 2 plus e to the x, and then differentiating this inside we get 2x minus 2, like such. Let's go back simplifying this a bit. So x squared minus 2x plus 2 plus 2x minus 2. Cancel, 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 so we get e to the x squared, like such. It's a stationary point, so we can say it's equal to 0. Note that e to the x can never be equal to 0, so that means x squared will be equal to 0. So therefore x is equal to 0. This is when the stationary point occurs, okay? So that's when we found it, that's the stationary point. However, we just determine its nature. This means, is it a maximum, is it a minimum, or is it a point of inflection? The way we go about showing it is d squared by dy. We need to differentiate it again. So differentiating this term here, once again product rule, e to the x squared plus e to the x 2x, like such. So we have e to the x squared plus 2x, like this, okay? So what we have to do is just place x is 0 into here. So if we put x is 0, e to the 0 is 0 plus 0, which is this e to the 0, which is just 1, okay? 1 means that sorry, it's 0, sorry, I made a mistake, so it's 0. If it's 0, that means it's neither bigger than or less than, so it's a point of inflection, okay? So this is when the point of inflection is a stationary point, because we set it equal to 0, as you can see here, right? So this point of inflection is a stationary point. However, there are also points of inflection which aren't stationary point, in which case we can't find them, right? Because if we make it dy by dx is 0, that's automatically going to be a stationary point. So in part B, they're asking us to find non-stationary points of inflection, okay? The way we go about doing it is looking at the second derivative. So we just differentiated earlier, d squared y by dx squared is equal to e to the x squared plus 2x, like this, okay? We know that 0 is a point of inflection, okay? So we can just say, look at this equation here and see when will it change signs, meaning when will it turn positive, when will it be negative. So I can say, the way we show about doing that is just maybe factorizing it. You can have x plus 2, e to the x plus 2, like this, okay? The reason why I did this was because even though it's not a non-stationary point of inflection, all points of inflection, the second derivative is equal to 0. Even though the first one might not be equal to 0, the second one is always equal to 0. So if I make it equal to 0, that means that either x is going to be 0 or x is going to be negative 2. Okay? This one is the stationary point of inflection, and this one here is the non-stationary point of inflection, as we found earlier. Okay? So this shows that it's a point of inflection. Okay? Right. We can't just leave it like this because we won't get all the marks, okay? So the way we show it is looking at the second derivative either side of minus 2. So what I can say is, if x is like negative 1, then if I replace, then the second derivative, if I replace it into that, negative 1, we get e to the negative 1, we have negative 1, 1 minus 2 is minus 1, so it's going to be minus 1, so it's going to be negative e to the negative 1, which is less than 0. Let's go to the other side, so x is negative 3. So therefore, the second derivative, dx squared y by dx squared, is going to be e to the negative 3, and then putting minus 3 into here, 9 minus 6 is 3. This one is bigger than 0. So as you can see, either side of this point of inflection, the second derivative changes signs. It goes from negative to positive. This shows that it is a point of inflection, okay? As I said, in the exam, you can't just leave it like this. You can't just say, oh, well, it's equal to 0, so I find x is negative 2. This is the way you show it's a point of inflection. This is for when it's a non-stationary point of inflection. For a stationary one, I can just leave it like this here. This is perfectly fine to do. But for a non-stationary one, I need to show either side of the point of inflection. Right, so this is all the differentiation topics and difficult things I think students might struggle most with. Just let us know in the comments below what other topics you want us to cover, and we'll try and get those videos up for you before the exam.